Okay, so last time we started talking about inverse trigonometric functions, starting with the sine function. And one detail that can be a little tricky about inverse functions is that we have to worry about what domain we use, because we have to ensure that our function is going to be one-to-one and therefore invertible. So it actually does have an inverse. For the sine function, we made this choice. We restricted our domain down to just minus pi over 2 up to positive pi over 2. So the reason why is if we continued off to the right any further, we would start sloping back downwards, and then we would fail the horizontal line test up here. And the same thing if we continued on in the leftward direction, we would start to fail the horizontal line test. So one thing that I didn't mention last time, but I should mention before we go too much further, is that it's possible to choose different domains for your sine function to get your invertible function. We chose this particular segment, but you could have chosen the segment from, let's say, pi over 2 down to 3 pi over 2, so the segment that slopes down to minus 1. And we know that this pattern is going to continue forever. So if we go off to the left or the right, this pattern will continue, right? It's just the sine wave function. So you could have chosen any of those segments anywhere along the sine function. This particular choice, the minus pi over 2 to pi over 2, I think is the most common one. And it's the one that you'll see in this textbook and I think most of your other math classes. But that choice does have a consequence. It means that our inverse function, sine inverse or arcsine, depending on which way you want to call it, the range of that is going to match the domain that we chose for sine. So the possible angles that can come out of arcsine are always between minus pi over 2 and positive pi over 2. Okay. And then we also talked about cosine and its inverse arc cosine. We made a slightly different choice of domain for cosine. So this choice corresponds to the upper half of the circle, whereas the sine choice corresponded to the right half of the circle, the unit circle. But when we made that choice, we still get something that's one-to-one. If we draw horizontal lines across it, we'll only intersect at most once. Okay, so this means the range of the inverse of sine, the range of arc cosine, is always between 0 and pi. So any angle that comes out of this function is always going to correspond to the upper half of the circle. Let's see, and then we practiced a little bit finding angles, and then the big result, the big thing that we did last time was we found the derivative of arc cosine using this formula for inverse derivatives from section 7.1. And I can flip back here to our new derivative rules. I gave you the derivative for arcsine, and this particular version has a u plugged in, so as if there was a function inside of arcsine. So you get 1 over the square root of 1 minus u squared, and then du dx because of the chain rule. And then arc cosine is very similar to arcsine. Its derivative just gets a minus sign. It's the only difference. And this derivative rule leads to an integral rule. So if you put an integral on both sides, you get rid of the derivative, essentially. So you reverse it. This particular version that I gave you has an extra constant a in it, because you'll often see integrals with some number here other than 1. And this rule lets us deal with that. It tells us what to do with that constant. It shows up in the denominator inside of the arcsine function. And then there's a few technical details which we mentioned last time, like for the derivatives, the function that you're plugging into arcsine needs to stay between plus and minus 1. And for the integral, your function needs to stay less than, your function squared needs to stay less than a squared. So basically, I'm saying that we can't ever divide by 0, and we also don't want to try to take square roots of negative numbers in the denominator here. That's what this helps us avoid. Okay, so that was all review from last time. Does anyone have questions over that material before we do a few examples? Okay, so let's get to this derivative example. It's important that you are comfortable with both notations for arcsine, either written as sine inverse or actually written out with arcsine. They mean the same thing. So for this one, we're going to use our derivative rule for arcsine. This one. So we take whatever we find inside of arcsine, we plug it in down there, and then the chain rule says we also need the inner derivative, the du dx. In this particular case, our u, the function inside of arcsine, is 3x squared. And that's going to get squared itself, and it should also be underneath a square root with a 1 on top. And then we need the derivative of this guy. So we need the derivative with respect to x of 3x squared. What is this derivative of 3x squared?
6x.
6x, good. So underneath the square root, we have 1 minus 9x to the 4th power, and on the top we get a 6x. Good. Any questions over that first derivative? Okay, so up next is an integral, and we can look back to our integral rule to interpret what we should do. So here's the rule. It's an integral for du over the square root of a squared minus u squared. And what we need to do is identify what the functions a, or what the constant a and the function u are. So this one is relatively simple. We don't have to do much work. Our a is just going to be 1, because 1 is the same as 1 squared. And our u is just x, because we have x squared sitting here. So this particular integral doesn't involve much extra work. We can plug 1 in for a and x in for u, and we get the arcsine of x, or x over 1. But for this particular integral, we have a definite integral, so we still have to worry about our limits of integration from 1/2 up to the square root 2 over 2. So that means we're going to have to think for a minute and remember what arcsine of square root 2 over 2 is, and also what arcsine of 1/2 is. So what is arcsine of square root 2 over 2? What angle gives sine theta equals square root 2 over 2? That's what I'm really asking. What angle should go here?
Pi over 4.
Pi over 4, right, good. What about arcsine of 1/2? What angle corresponds to sine theta equals 1/2? Pi over 6, right. The answer was in the...
Pi over 6.
Good. Okay, so this is our solution. We should probably get a common denominator to finish this off. Let's see, I'll work to the right. The common denominator between 4 and 6 should be 12, of course. So this becomes a 3 pi, and this becomes a 2 pi. That's all over 12. We have to multiply by 3 to get 12 in the denominator, and this one will have to multiply by 2 on the top and the bottom to get 12 in the denominator. That's where this comes from. So the final answer is pi over 12. Any questions over the integral? Okay, so now we'll do one that's a little bit more challenging, because instead of just 1 minus x squared in the denominator, we now have something a little bit more complicated. We have the square root of 5 minus 16x squared. And the idea for this, well, there's a few ways you could think about it. We're still going to use the same rule, but we need to identify what a and the function u are. So what I would like to do, probably for the first one, is we know that a squared is going to be this constant here. So let's just write that. A squared equals 5. And then u squared is going to be this function, the 16 minus, or sorry, just 16x squared. So if a squared is equal to 5, and we know that a should be greater than 0, what should a actually be? Well, it's just the square root, right? The positive square root. It's the square root of 5. And we should also take the positive square root for u. This time we'll get a 4x. Okay, so now we can plug the constant a, and the function u into our integral rule. We get arcsine of u over a. That'll be 4x over the square root of 5. And then since this was an indefinite integral, we need to be sure to add a constant on the end. But actually, you might be able to see that there was a small mistake somewhere along the way. Can anyone find it? Oh, okay. Yeah, there is a square root in my denominator. Some some teachers they force you to write, what do they call them? Rationalized denominators. So you would multiply by square root 5 over square root of 5 to get rid of that one in the denominator. We don't really care about the square root in the bottom of the fraction for this particular class. The thing that I'm worried about is what happened to this dx. Because you see in my rule, I don't have a dx on top, I actually have a du. So we didn't completely finish our u substitution. We'll have to go back and figure out what du was. So u was 4x, so du is the derivative of that, 4 times dx. So that means dx itself is actually equal to du over 4. This means that when I was doing my integral, where I had a dx, I should actually add an extra constant of 1/4. So that will carry through to the front of my arc sign. This extra 1/4 here. So when you're using this new integral rule, you still have to be careful with your u substitution. You still have to follow through all of the steps of u substitutions. Okay, so any questions over this last or this third integral? Okay, so since it sounds like there aren't any questions, let's go ahead and move on from sine and cosine to the next trig function that I want to talk about in the section, the tangent function. And just like for sine and cosine, I want to go over to a nice little graphing tool so that we can look at a picture. So everyone's probably familiar with tangent. It has this repeating pattern of vertical asymptotes. So you might remember it has a vertical asymptote at pi over 2 and also minus pi over 2. Maybe we can graph some of those vertical asymptotes in. Make those lines dotted so they don't stand out quite as much. So tangent has this repeated vertical asymptote pattern. And what we have to do, if we're going to talk about the inverse of tangent in a second, is figure out a domain to restrict tangent to in order to get a one-to-one function that passes the horizontal line test. So right now, if I draw a horizontal line anywhere, let's say y equals 1, then this is going to cross my tangent function an infinite number of times. This will just continue off to the right and the left. And no matter where I move this horizontal line up or down, we're still going to have the same problem. So let's start trying to restrict down my tangent function. Okay. So I've added a few sliders so that we can experiment. So what I want to do is start moving in my slider. So we can see it's getting better. We're not crossing quite as many times. And we can also move this one in from the right. And gradually get better and better so that we're not crossing so many times. And at this point, you can see my horizontal line only crosses tangent a single time. But if I moved that up to this little extra hanging bit, then we would still have a problem. Let's move that in so that the hanging bit disappears, or at least on this graph. And we have the same problem down at the bottom with this little bit. If I can move my horizontal line down there. So we need to move that in as well. And this looks pretty good. So probably at this point, you can tell what my limits should be for A and B. They should actually match up with my blue vertical lines, my vertical asymptotes. So I need to get this in between minus pi over 2 and positive pi over 2. And now, no matter where I move my horizontal line, we're only going to cross the graph of tangent a single time. Okay, so that tells us the domain of tangent that we need to restrict to. And then what's going to happen with the inverse function, maybe get rid of this horizontal line, is we're going to mirror tangent across the line y equals x. Make that a different color maybe. There we go. So let's graph in arctangent. And there it is. So that one's in green too. Let's make it red, or the black will work. Okay, so arctangent is in black. The original tangent is in red that we've restricted down to this domain. And you can see that the black curve is the same as the red curve, but mirrored across this line, the green hashed line, y equals x. So that's tangent and arctangent in a nutshell. We should go back to the paper maybe and consider things like the domain and the range. Oops. So tangent, I'm restricting down in between minus pi over 2 and positive pi over 2. That's where I add vertical asymptotes. So it looks something like this. Maybe we can write its domain and range while we're here. Oh, it sounds like some of you might be having some connectivity issues. I guess that can happen when it's raining if there's a satellite connection somewhere along your internet connection route. I will be posting the recording of this later in case you missed part of it. So for tangent, we restricted the domain in between minus pi over 2 and positive pi over 2. And you'll notice that I'm using parentheses this time because of the vertical asymptotes. We can't actually include those particular points. And the range of tangent in this interval goes from minus infinity all the way up to positive infinity. And then the inverse function switches everything around. The vertical asymptotes become horizontal asymptotes. Something like this. And it also switches the domain and range. Let's see if I can put it in down here. So the domain is the old range, minus infinity, positive infinity. The new range of arctangent is the old domain of our tangent function at minus pi over 2 up to positive pi over 2. And like I've been saying, you can think about this as tangent inverse or write out arctangent. They mean the same thing. So there are a few features that you need to remember about arctangent, primarily these horizontal asymptotes. So if you take the limit as x goes to infinity, you're going to level out to pi over 2. If you took a limit as x goes to minus infinity down this direction, you would level out to minus pi over 2. So keep that in mind about arctangent. Are there any questions before we talk about the derivative or some other properties of arctangent? Okay, so let's do a few quick examples. We'll start by finding the arctangent of minus square root 3. So this means I'm looking for the angle, oops, tangent this time. I'm looking for the angle that gives me tangent theta equals minus square root of 3. Does anyone know what angle that would be? Remember to always think back to the unit circle. And for the tangent inverse, we're going to be thinking about angles over here on the right half of the circle. Okay, so looks like someone in the comments said pi over 3, so that would be up here. So that would give us a positive square root of 3 from tangent. Because this point is 1/2 square root 3 over 2. Good, so it's the corresponding angle in the lower half of the circle minus pi over 3. Because this one is positive 1/2 for cosine, but then minus square root 3 over 2 for sine. That's where we get the minus sign from. Good. What about arctangent of 1? So which angle theta solves this equation? Tangent theta equals 1.
Pi over 4?
Pi over 4, right. So we're looking for the point where sine and cosine are equal to each other. or the horizontal and the vertical are the same. Good. Pi over 4. Okay, so that's how arctangent works. You have to think a little backwards. So if you're trying to figure out arctangent of a number, you're really trying to solve an equation with tangent in it. Okay, I guess before I go on, I should ask if there are any questions. Okay. So now let's do the derivative of arctangent the same way that we found the derivative of sine last time. So we need to go back to the formula for the derivative of an inverse. Oops. Try that again. Just need an x here. So this is the fraction 1 over, and then you plug the inverse into the derivative of f. And in this case, our function f is going to be tangent, and its inverse is arctangent. So what is the derivative of tangent? Someone? Secant squared, right? So we're going to be plugging in arctangent into secant squared. And just like last time, I want to use one of the Pythagorean identities. This is the one where tangent squared plus 1 is equal to secant squared. This just comes from the Pythagorean theorem. Okay. So if this particular formula seems unfamiliar to you, it's probably a good idea to go back and review some of your trigonometry. Like last time we used the formula sine squared plus cosine squared equals 1. And this is just another version of that you should be familiar with. So what I want to do is think about secant squared as tangent squared plus 1. So since arctangent was inside of my secant, it's now going to go inside of the tangent here on the left side. So I now have a tangent squared of arctangent, and then plus 1 in the denominator, and then 1 up top in the numerator. And this is where the little bit of magic happens. We're taking a tangent of an arctangent, so those two functions cancel each other. So what we're left with overall is just the x squared plus 1 from the denominator, and just carry the 1 all the way through to the end from the numerator. Okay, so any questions We now have the derivative of tangent. Any questions over what we did? No? Okay, so let me go to the back of this page where I have some more room and write out that as a rule. So we have a new derivative rule. Okay. And it's really important that whenever you see a new derivative rule in class or a new integral rule, that you immediately put in some effort to try to remember it, to memorize it, in fact. Because when you're working on an exam where you only have a limited amount of time, you don't want to have to, well, you don't want to have to spend too much time thinking about how to do the easy stuff, and this one eventually will feel like one of those easy things. Okay, so the derivative of arctangent of u is 1 over 1 plus u squared, and I'm thinking of this as a chain rule, so I also need a du dx at the end. And reversing this rule gives me a integral rule, because integrals are just the opposite of derivatives. For this one, I'm going to add an extra constant n, just like we did for sine. Let me show you where it's going to go. So I'm going to put it in the denominator. In place of 1, I'm going to put an a squared. Okay. And this constant is going to move actually to the front of the tangent and also to the inside. So it'll show up here, a 1 over a, and then it'll show up inside of the arctangent as well, u over a. And then add your constant since this is an indefinite integral. Okay, so two new rules, a derivative rule and an integral rule that you need to add to your memory bank, your calculus memory bank. Leave those there for a second. So maybe you can write them down. Okay. So let's move on to the examples here. So the first one is a relatively simple derivative. We have a tangent inverse. And again, you need to be comfortable thinking about tangent inverse as either this tangent with the -1 to signify the inverse, or arctangent, because they both mean the same thing. So we're going to apply our derivative rule that we just saw, where our u is going to be x to the 5th power. Okay, so we get 1 over x to the 5th squared. That's going where u was, and then we're adding 1 in the denominator. And then we need the derivative of u. What's the derivative of x to the fifth power?
5x to the fourth.
Good. 5x to the fourth from the power rule. And then in the denominator, x to the fifth squared gives us x to the 10th power, and then plus 1. Good. So any questions over finding this first derivative? Okay, so since there aren't any questions, let's move right along to this integral. So we're going to integrate dx over 4 plus 3x squared. So we have a constant other than 1 in the denominator. That's why I wrote the rule for the integral in a slightly more complicated way. Our a squared in this particular case is going to be 4. And then our u squared is going to be the function 3x squared. So what is a equal to? Anyone?
2.
2. And what is u equal to? Well, this one might be a little bit tricky. This is u squared is equal to 3x squared. So we have to think about taking the square root of the right-hand side. So what we'll get is a square root of 3 and then an x. And let's try not to make the same mistake that we made last time, where we forgot to finish our u substitution. Let's go ahead and find du. That'll be the derivative of this guy, the square root of 3, times dx. Okay. So where I have the dx, I'm going to actually write du divided by the square root of 3. Okay, so it's a squared minus u squared, or sorry, a squared plus u squared in this one. And then we have the du over square root 3 up top. Okay, so the square root is going to move to the front. And then we can use our new integral rule. Let's see, I guess it's on the back of this page. Just remind you what it looked like. So a shows up here in the fraction, and underneath u inside of the arctangent. So this means we need a 1/2, 1 over a, and then arctangent of u over a. So that's square root 3x over 2 inside of arctangent. And then we add a constant. Since this is an indefinite integral. Any questions over that example? Okay, so I think that is a good stopping point for today. Next time, we will move on to talking about the inverse of secant. So if you don't have any more questions for me, I will see you guys tomorrow morning.
Thank you.